Okay, so let's get started. How's our progress on programming assignment 1? Who's all done with greedy scheduling? Greedy scheduling all done. How many have at least started greedy scheduling? What are we stuck on for greedy scheduling? What are some places we got stuck on greedy scheduling for? Okay, so for those who are done with greedy scheduling, how did you solve it? Yeah. Okay, so the basic approach is a selection sort, right? And that's perfectly fine for greedy scheduling. You can even read through the file multiple times, right? So you're trying to schedule a room. You set your time you're willing to schedule to, starting from time equals 0. Look at all the jobs that finish at time equals 0. Pick the best one. And if there are none, keep going, right? So a selection sort works perfectly fine for greedy scheduling. Right? Okay, I'm a little bit concerned about how many are done with greedy scheduling because it should be pretty straightforward based on the code that's given out there. So you don't want to be scrambling, okay? So I would have expected by today greedy scheduling is all done. And then through today, you should have everything that you need to be done with the second part, edit distance. So by Tuesday's class, if you're not done with edit distance, I would think that you're really in the stress out zone at that point. All right. Okay. And besides that, there's a quiz due tomorrow. So the quiz is stuff that was already covered through last week and maybe a little bit of Tuesday. So all fair game. Don't fall behind. Okay. So recap of what we saw on Tuesday. We looked at fixed length arrays, and for arrays that are dynamically sized, so before the program runtime, you don't know how big the array is going to be. All of that has to live on the heap. And heap is a separate portion of the computer memory, which is useful for storing data that is dynamically sized. And in order to work with memory on the heap, we need to use two special functions in C called malloc and free. So this malloc thing, is this completely new to C? Have we seen something vaguely similar to this in Java? Yeah. So new, what does new mean in Java? When do you have to use new in Java? When you're creating an instance of a class. When you're trying to create an instance of an object from a class, invoking the constructor of the class. Right? And underlying all that, when you call the constructor, what it really is doing in Java is it's going to the heap, and it's allocating the memory you need to plop down that object, right? That instance of a class. So this is not completely new, right? We've actually encountered before in Java something very analogous to malloc. How about free? Have we seen something like free in Java before? Yeah. Yeah, so in Java, you don't have to worry about when the object has to go away, right? You can, in programming Java, you can keep plopping down new objects throughout your heap, all you want. And Java has a very nice facility called garbage collection, which will keep track of all your objects. If an object is no longer referenceable, right, the scope of that object has disappeared, the garbage collector comes through and deallocates the memory for you. In C, C is a more primitive language. We have to do this manually. We talked about how pointers and arrays really are built up using the same mechanisms. The name of array is really a pointer to the beginning of the array. And so using that knowledge, in our first day of class, we talked about how the arguments come into the program as an array of strings. So with that, now that we know that arrays really are also implemented using pointers, pointing to the beginning of the array, now we understand why really these are kind of the same thing. Okay, any questions up to this point? So that's recap. New material for today. Right, so new material for today, let's look at 2D arrays. Right, so in the pointers lab, there's a portion of the code called 2D arrays. And in addition to that, I've created some new example here of a fixed length 2D array. So this is an array where we know how many rows and how many columns you need to instantiate this array. And you can even populate the array by this array initialization syntax here. So you can nest the curly braces to create an array with these elements all already created. The dimension of this array is going to be 2 rows times 3 columns. And what we're going to experiment now is we're going to, again, try drawing a diagram for all of this. So back to our pointers lab all over again, pointers lab picture. We're getting a lot of use out of this spreadsheet. Let me make some space to write down these notes. So first task, I've got highlighted line 111, right? So as always, every line of code, we can draw a correct picture to understand what's going on. What's the data type of this new element that we want to write down? Int? Yeah.
Would it be int
Int pointer once? 2 times, right? So here is now an example where we have pointers to pointers doing something useful, right? Previously, somebody asked a good question, right? When are pointers to pointer useful? Why do you want to grab a pointer reference to a pointer? And our first answer to that was you have things like linked lists. We're going through the linked lists. You're going to pointer to pointer to pointer to pointer. And here's a different use case, a different way in which doubly referenced pointers are useful, right? The data type here is a pointer to an integer. What's the name of the data type? Well, what's the name of the variable?
Array demo 2D.
Yeah, we've got array demo 2D. And where is this in memory? We don't know, right? But we can inspect its contents, right? So we can ask to print out, hey, what's the value of array demo 2D? Treating it as a pointer. So what is the value of array demo 2D? So let's run that program. Equals. Let's run the program. And it prints out array demo 2D is this pointer here. So where does this go in our picture? Well, it's going to be a box of 8 cells, 8 bytes. These 8 bytes occupying 8 cells. And, well, where does this go? Well, it's a pointer. Where does it point to? Somewhere in memory, right? So we can go chase down that location a couple different ways, right? So we want to now go inspect where is this, where at this location of memory, what's its contents? What are a couple ways we can do that? I want to go look at what's at this location of memory. Yeah.
Use star array demo?
Yeah, star, going from address to contents. So let's print that out. Another way, we could also do this. So let's make the program, run the program, and there you go, right? We've got a couple of different equivalent things that it's done. So we went to this location of memory, asked, okay, where does this point to? Are those the same value? Did I mess up somewhere? Oh, it is the same value. Okay, interesting. All right, so it says, well, what's there is this value here. So wherever this was pointing to, it points to this location. And now let's take a look at what's the next item, right? So what's our way we can do the next item here? A couple different ways, two equivalent ways, yeah.
You can do star array demo 2D plus 1.
Okay, so let's do that. Right, so again, semantics, right? What does this plus mean here? Is it just plain old addition? Yeah.
We go into the next address available, next byte available.
Now, a trick question. There's a trick here. Am I parenthesizing this correctly?
Oh, wait, no, it's the next beat.
Yeah, right? So keep in mind, order of precedence, right? The star operator, the dereferencing operator, binds very closely. So the program is going to look at what I've highlighted on the code here, and it will say, yeah, go ahead, dereference array demo 2D, and then plus 1 to that. So we want to change that around, right? We want to parenthesize this to make sure this really means the next valid pointer location. So let's print that out. And another equivalent way, what's this equivalent to? Yeah.
Array demo 2D with brackets 1.
Yeah, access the first element in that array. Right, so let's also print that out. Okay, shall we run the program and see what happens? Okay, so it says that the subsequent pointer value in our picture, so let's go to our picture, is going to look like this. And how tall is it supposed to be stored in? Same thing, 8 bytes. 8 bytes. We'll merge and center. And again, every time we run the program, the values change around. So let's grab that just so that this is consistent. Okay, anybody want to take a look at these two pointers values and what's the difference between them? What's the increment between these two pointer values? Right, the first one ends with 8E0, second one ends in 8EC. What's the difference? Yeah. 1 byte. Close. Another guess? Yeah, over there. 12. How do you get 12? What does 0 to C mean? How'd you figure that? Good, right? Hexadecimal. A is 10, B is 11, C is 12. So the difference between this pointer value and this pointer value is 12 more bytes further down, right? So how do we figure, why is it 12 bytes further down? Yeah.
It's because you have three integer values being stored in one integer 4 bytes.
Okay. So let's examine this a little bit, right? So I think I'm losing you. Let's do this more rigorously, right? Let's chase this pointer once again. How do we chase this pointer once again? Right? This is telling us to point to this location here. Let's go look at the contents at that location.
Use another star.
Let's use another star. So this time, let's say star star, array demo 2D. And what's that equivalent to? Yeah.
I'm gonna say 1.
1, okay. It will print 1, that's right. What's another way to get it to print 1? Where's the 1 in this array here? 2D array. Yeah. It's at array index 0, 0, right? Coordinate 0, 0. So we could also do 0, 0. Right, so let's go ahead and run. Okay. So the compiler is saying that I'm trying to print it as a pointer, which is incorrect, right? So it's able to keep track of the data types and sees that, okay, we've dereferenced a integer pointer twice, so you're left with just a plain old integer type. Printing out plain old integer types, you should use %d. And yeah, so what it's saying is if we chase this pointer twice, it is going to point to, at this location in memory, there is the value 1 stored there. And what's the C nomenclature to get to here? It is int 0. Sorry about this. Int array demo 2D 0, 0 stored there. Good. Right, and where do you think 2 is stored in this picture? Yeah, just shout it out.
This could be at the address value ending with 84.
At address value ending in 8E4, good. Right, and why 4?
Because integer 1 takes up 4 bytes, so the next index is going to be 4 bytes.
So 8E4 is going to be that 2 there. Keep going. 8E8. Come on. Is going to be the 3. And then finally, we're ready for the 12, right? 8E12. How would you write down 8E12? Yeah, so in hexadecimal, it would just be C. So at location 8EC, we expect 4, right? And so 5 is stored there, 6 is stored there, and that's it. So what's the takeaway here? How does C store 2D arrays? Yeah.
It's stored as one continuous block of one array next to another array.
Yeah, so it just takes the arrays, it goes one array to another, to another, to another. It just chains the rows together, right? And so by this, it also means that it is valid, right? It is valid to ask, what is the value of array demo 2D and then index only one time, right? You index it only one time. This refers to row 0. And what is that? What is the data type of that? Well, the data type of that is a pointer, right? It points to where row 0 begins. Where does row 1 begin? Well, it's valid to ask that. Array demo bracket 1 that asks, where does row 1 begin? Yeah.
So by using pointers instead of like the regular braces, we could just use only one for loop to iterate through the double array instead of needing two.
Okay, that's a good question. So your question is, if you used only pointer into arithmetic, would it be possible to iterate through a 2D array using only one for loop? Who thinks you can? You mean your raise hand means you think you can? Okay, yeah, you can. Is that a good idea? Yeah, stylistically it's messy, right? Even if you can do it, because that's what's underlying the implementation, it will be difficult to understand the code, right? So you shouldn't do it. Okay, so that's fixed length arrays, right? This is an array where we already know the size of the array. And suppose you don't know what the size of the array is. Well, we already studied how to allocate the memory needed for an array. And really all of this is just like before, but now we do all of this in the heap instead. Okay, so same approach, and we're going to go more quickly through this here because this is just extrapolating everything that we know so far, right? The data type here is going to be int pointer pointer. And this time around, instead of invoking malloc, I'm going to call this function called calloc, right, which is very closely related to malloc, right? And I encourage you to use calloc instead. So the format of calloc here is, instead of giving it a single argument, instead what you do is you give it two arguments. The first is the multiplier of how many of those elements you need. Then you provide the size of each element. Right, so this just kind of cleans it up a little bit. This would just be like malloc if you multiply these two arguments together. But a nice thing that calloc also provides is it also guarantees that after callocing, it will zero the memory for you, right? So the contents of that piece of memory in the heap it gives you will already be zeroed out, right, with no data inside it. Very good, right? So we can iterate through that level of the pointer. Who wants to take a look at what's happening on these lines here and explain what's going on here? Yeah.
So for each row, essentially, for each first pointer, you're going to allocate more memory for the columns.
Good, right? So should we diagram this, or are we okay with figuring out what that looks like? Who wants some more diagramming? Okay, who doesn't want diagramming? Okay, the people who want diagramming win. Okay, so let's diagram, right? So we got line 128, quickly, and just shout it out, right? No raising hands. Data type.
Data type int2 star.
Int star star. Name of the variable?
Array underscore 2D.
Where is it in memory? We don't know, but we could ask. If we run the program up to that point, it will tell us where to chase that down. Good. And same thing, we now enter the loop, and it says, starting at the location pointed to at array 2D. From there, each valid location further allocate more pointers, right, and print those out. So we can diagram everything up to this point. So let me stop the program at line 135. But just to be careful, right, I'm going to end the program at 140, but because those have mallocs in there, memory allocations, I want to make sure that I free them before I end the program, otherwise I get an error. Let's make and run, and let's diagram what the printout is telling us, right? So our relevant lines here are these 4 lines of printout here. So it says that it created array 2D. Its value is this, 0x6 something. So already, right, just what did we notice before? There's a pretty significant difference about this type of pointer compared to the pointers that we've seen before. What's the difference? Just visually. Yeah. Yeah, this is a lot smaller than this pointer value, right? This is pointing to something somewhere very different in memory. It's up here in the heap. So we scroll up, all the way up, past the stack, back into the heap. At this location, we shall found our array 2D, right? And then, what do we store at that location, right? So we've created this array, 2D, pointing at this location. And how big of a chunk of space have we allocated for us? Right? How do we see that? What am I referring to? What does this evaluate to? How big of a piece of memory? Yeah. Is it 8? So how big is the array that we want? 3 times 8, so 3 pointers worth of memory. How much space is needed to store 3 pointers worth of memory? 24, right? So, all right, let's go. 1, 2, 3, 4. 1, 2, 3, 4. This is 2DDS. Let me just draw a bunch of these. So starting at line 11 plus 24, 35. So I want this box here to be 35. And keep going, keep going, keep going, keep going. There, roughly. That's 24 bytes. And what do we put in these 24 bytes? This loop here, right? It's saying that at this location, which is pointed to by array 2D, give me these 3 pointers, right? On each iteration of this loop, it will return pointer addresses, which we will store here. And we can go to our printout to take a look at what this printf statement tells us. So let's look. So it says, at array 2D, the first element, index 0, store this pointer value here. And how much space does it take to store it? 8 bytes. 4, 1, 2, 3, 4. Merge and center. Let me prepare the next space. 1, 2, 3, 4. 1, 2, 3, 4. Merge and center. 1, 2, 3, 4. 1, 2, 3, 4. Hooray, it's the same size. Good. So what do we store next? Pointer to row index 1, and then pointer to row index 2. Good. Good. And where do these point to? Just visually.
The first one points before the array.
So reading from the most significant bits now, right? So this address here was 0x603. So this starts at 0x602, right? So it's yet farther higher above, right? So somewhere farther up here, it will now give us the space to store each row of the array, right? So it allocated for us addresses further up top. Right, so that's exactly what this is doing here. And the next segment of code, right, so pause here, right? Are we okay with how this 2D array is set up? Right, it's the same picture, but this time around, we're just doing the same thing up in the heap. Yeah?
So I know before it was going up by 4 bytes, putting integers instead of 4 bytes, but in this case, now it's going by 20. Is that just because of the extra space, or is there something else to it?
Good question, right? So let's chase that question, right? So how much space is it allocating per row? 5, 0 minus 3, 0. Is it 32? How do you figure 32?
Because these numbers are in hexadecimal, so each place has like 16 values. So if the place after it goes up by 2, then that instead of 20, it corresponds to 32.
Good. Right, so let me just repeat that. That's correct, right? So the amount of space that's been allocated, it's 5, 0 minus 3, 0. Right? But this is not decimal, though, right? It's 5, 0 in hexadecimal minus 3, 0 in hexadecimal. The difference of 2 in that second digit is actually 2 times 16, right? Because this is the 16th digit. So this is 32 bytes that have been given to each row. 32 bytes for each row. And does that make any sense for how much space is allocated here? Right? This is kind of a trick question now. We're into new territory. How much space will this calc request? Yeah. 12 bytes. How do you figure 12 bytes? So array size is 3. So the number of columns per row we want is 3. Each integer is 4 bytes. So really this only needs 12. Right? So we just need 12 bytes to store this row. Why is the C programming giving us 32? Yeah. A buffer, yeah, that's a good rationale. Yeah, it's a buffer. There's other metadata it has to store, right? So for example, when we run a program, right, and we overrun what is been correctly mallocked, how does the program know you're reading into memory that has not been mallocked? Well, it's enabled because for every malloc call here, for every calloc call, it requires a little bit more extra space to keep track of some metadata. And I don't know the details, but in this case, in order to keep track of all that data, it needed 12 bytes to store our integers, and then some more space to store the metadata, and so it allocated the next row 32 bytes later. Right, so there's a qualitative difference now, right? There's a qualitative difference. For dynamically sized arrays in the heap, are rows always going to be contiguous? Yeah.
So we're allocated 32 bytes. We're using up 12. So that extra 20 bytes, is all of that going to be used up by the metadata you're talking about, or will some?
Could be any kind of reasons. Could be because of address sanitizer needs to write stuff down. Could be because it just wanted to pad things in nice even increments. It's up to the implementation of the compiler.
Yeah, but will it still use up all of it, or will some of it?
Yeah, it'll use up all of it. Yeah.
So how much, would it be less space efficient to use this over like a fixed array though?
So good question, right? Is this somehow less space efficient than if we did this more carefully? Right, the answer is sure, we're wasting some space here, right? We could, instead of writing these 2D arrays, somebody suggested, well, 2D arrays can be perfectly represented as just one long 1D array. That would be more space efficient, but it's at the cost of writing code that is concise and clear. Yeah?
And to answer the question from before, I would assume it wouldn't be continuous then, right? Since it has that space for the functions.
Yep, so at this point, right, these values for the arrays, they're no longer going to be contiguous. Because I'll write down one row, there's going to be a gap, let's say of 20 bytes in this case, but it's not guaranteed. And then it'll write down the second row, there's going to be another gap, and then write down the third row. All right. So that's basically it on 2D arrays. We can go ahead and let the program run just to see that the program runs through. And there's memory leaks. Why is there memory leaks? Yeah, I didn't delete this return. Yeah, so the program just runs through, and then the rest of the code is just some mandatory demonstrating that, yeah, no problem, we can read and write to it. That's not super interesting. Okay, so new territory. So we've seen how pointers allow us to create arrays. The next lesson is all about how pointers allow us to build functions and allow us to pass data into and out of functions. So we will start with a little puzzle in lesson 7, where I've got this function called swap pass by values. And I've got two integers, arguments a and b, 211 and 422, getting passed by values. And I've got all this additional stuff printing out, nothing up my sleeve, right? Just printing out the values where they are stored. The interesting thing is going on inside swap pass by values, so let's look at that source code. It's farther down in the source code in swap pass by values. So quick teaching moment here. The C program is reading through this code, or the compiler is reading through this code. How does it know the function prototype of swap pass by values? How does it know that this is a function? Text? Is it text? Yeah, it's text. That's right. Yeah.
You'd have to declare the function header before the message runs.
Good, right? Then this is common to Java. What does it mean to declare a function versus define a function?
Like declaring a function, it's you're describing like the name and like any parameters that it may take in, but you don't write out like the logic behind the method. And then defining a function is you're writing out the logic.
Very good, right? So let me just say that louder in case you didn't hear. So declaring a function has to take place before you invoke it, right? So here on line 168, I'm going to invoke swap pass by values. And the compiler is cool with that because up here, we might not have noticed before, but here I've defined the function, right? I defined swap pass by values as a function. Its shape, its signature, is that it takes two arguments in A and B, and it returns nothing. It returns void. How does swap pass by values work? Not telling you yet. Right? I'm just saying that there is this function. I'm simply saying that there is this function. If you want to know how to implement it, that comes later, right? And so I'm able to define the function farther down here on line 207. And what swap pass by values does is it again does some inspection of where A and B are stored, and it attempts to swap, right? Okay, maybe I spoiled it there, right? It swaps it. Okay, let's just pretend it swaps it, right? So it says temp equals B equals A equals temp. If this were Java, would this have worked? I see a very adamant head shake. Why wouldn't it have worked?
Because you're passing in, well, in Java it'd be a primitive type, so because you're just passing in the value of A and B, and not like, regardless of its memory address, it wouldn't actually update the value that you defined earlier.
Okay. So your intuition is correct, right? It doesn't work. The swap will fail. And this time around, because now we have pointers, we can really see what's going on, right? This is new, right? Maybe if you knew that this wouldn't work in Java, but you had to memorize all this stuff about like primitive data types won't work, but like objects will work. Why? Well, here's why, right? Now we can actually look at pointer values and study what's going on. So let me do some cleanup now. So on our spreadsheet, we're gonna move to the next tab called swapping. And let me just add a couple columns to make it look a lot more like what we had before, which is I've got several columns. One is called data type, another called variable name. And then the way I'm going to box all of this, I'm going to clean this up a little bit. Just bear with me here. The way I'm going to box all of this is, again, the heavy box only goes around real memory. Right? So the heavy box means actual memory addresses. And let me just clean all this up. So delete these rows. All right, here we go. So again, right, we have a methodology here of every line of code that we see, we could write down. What's happening in the memory. And right now, all of this is going to be, once again, in the part of the memory called the stack. Right, so we're on the stack. We are in the stack. And every line of code, we can write down what's happening in memory. So data type, we got integer. Variable name is A, and we're going to store 211 there. Takes up 4 bytes, we know that. Next line of code, 163, another integer. B, its value is 422. Very good. And then we're going to let the program run, right? The program running is going to tell us a little bit about the landscape here. Right? It'll tell us some information about where all of this is stored, right? So let's let the program run. So it tells us that A and B are 211, 422, no problem. And as promised, after executing swap pass by values, A and B are still 211, 422 in that order, right? So swapping did not happen, did not occur, did not succeed. It gives us the pointer addresses, which, just to be a little bit cleaner, let's print this out as pointer hexadecimals instead. think that's a little nicer. Right? And how do we interpret what this is? Just as a very quick review. What does ampersand do? Yeah, ampersand really just means address of the content, right? So look at what the address is. So this line of code will tell us what the address of A is, and we can jot that down. Right, so A was stored here, and B was stored at address here. Good. So then we have a couple more lines of printout here, right? Where did this come from? This was printed out from inside pass-by values, right? We can take a look at the source code. The next couple lines of printouts are from inside, calling in from inside swap pass-by values, and it also takes a look at where A and B are. And are they the same address? No, not really, right? And where is this address relative to what we had on the picture, right? So addresses grow bigger going down, right? 30, so B30, B40, but this one now is so A20, A30. Where is it relative to this picture? Yeah, it's above, right? Is it far above? No, just a little bit above, right? All right, it's just a little bit above. Come on. Merge. And merge. Good. Should we be exact about how much above it is? I don't think that's important, right? So somewhere above, we've got where A and B are stored inside swap pass-by values. So I've got this address. Do that. So normal formatting, good. And I've got this other address, which stores a copy of B. And int A is stored here, and B is stored here. So we've got 211 and 422. And I'm going to put a new box here indicating that we're kind of somewhere else in the memory now. So this new part of the memory, this is called a function call frame, right? So originally we were here in the main method. What was the function signature of main? Main returns int main. And all of this was the call frame for main. And now that we've called into swap pass by value, we're somewhere else now, right? We're now in swap pass by values. What's the function form signature of swap pass by values? Void, returns void. And swap pass by values. And this is the frame for swap pass by values. So anybody want to see this now and say, oh, that makes sense. This is like a stack. So in what way is this like a stack? Yeah. Good, right? So we called a function, and when we call that function, we piled some more memory on the stack, right? We've created a new frame, we push that frame onto the stack, and then once we're done with swap pass by values, we pop it off the stack. Last in, first out, right? So this is a underlying reason why this is called the stack. This is the stack of memory. It's the stack of function calls. And by calling a function, we create a frame, we put in all the arguments, and we do work inside this frame. So we can now progress, right? On this line of code, we can diagram this too. We're right now in swap pass by values, so what's the data type of this line of code? It's an int type. The name of the variable? Temp. Where is it in the memory? We don't know. We could ask, but it doesn't matter, right? It's going to be here somewhere in this frame for pass by values. And now we can run the code, right? We can progress through each line of this code and move stuff around. So what happens first? Temp takes on the value of B. B takes on the value of A, and A takes on the value of temp. Right, makes sense? So inside here, sure, A and B are now swapped. A equals 422, B equals 211. We're done. And we exit this frame. What happens next? Yeah. Good, okay, so as exiting the function, we're done with all this, right? So it's a stack, we pop the whole frame off. That's what we mean when we return from the function. So we exit swap pass by values, we go back to main now, and devastatingly enough, in main's A and B never changed. Nothing bothered to change here, right? So after exiting swap pass by values, here in main, we print A is still 211, B is still 422. So how do we, that's disappointing, right? So how might we actually build a correct swapping function to make it work? Yeah.
Like if you use pointers instead, even if they are the pointers that get changed die after the function is done, the actions that the pointers themselves like do, like if you use star, they will remain and you can use them.
Good. So the key idea is instead of passing values, we'll pass pointers instead. Okay, so that's intuitive. We can show that on the picture. Maybe a kind of useful question is, have we ever seen an example of this in Java? Right, if we had like a very rote, like 111, 112 exam question, that's just like, when does swapping work in Java? Or when does, maybe the question is, like, have we encountered something like this in Java before? Yeah, go for it. Okay, so in Java, if the function took in objects, then it would work. In Java, what's the difference between primitive data types and objects? Yeah.
Objects are like the variable names themselves. They're stored as references instead of primitive types.
Okay. So that's the next level thing, right? So give me some examples of primitive data types in Java. Primitives, yeah. What else? Int's a primitive, yeah. Union, okay. That's a good one. Anything else? Char, float, double. Yeah, all those are primitives. What's notably not a primitive? Is string a primitive? So in Java, the word string, is it capitalized? Yeah, and it's capitalized, and it's a subtle hint that string is a object type, right? Belongs to the class string. Well, whereas primitives are all lowercase int, lowercase char, right? And the secret thing is when you passed objects in Java, you're passing pointers, right? The references that we had in Java, that means exactly the same thing as pointers in C. The difference now is in Java, Java doesn't really let you print out what the value of that reference is. Doesn't mean much in Java. But here in C, pointers are just numbers, and we can print out what the values of the numbers are. Okay, so this time around, we're going to attempt a successful swap, this time around via this function called swap pass by references. And what's the difference between pass by reference and pass by values? Yeah.
We're taking in the address values and not the pointer values.
We're passing in the pointer values and then no longer the values themselves. Good. All right, so let's diagram this, right? We can run through the exact same code as before. Here we are in main. In main, we have A is 211, B is 422. We print them out, no problem. And now we're going to call into pass by references. What does it mean to call a function? We push onto the stack a new frame, and we build a new function frame. And those addresses are going to be lower than where we were at before, relative to main. Same thing, we can print out these statements, but what's different now? The data type is different, right? What's the data type this time that's being passed in?
Int star.
Yeah, we're passing in int star. And so there's another tweak to this picture. How much space does it take to store int star? Yeah, so subtly this is going to be taller. And the value here, the variable name is also different. It's called a pointer. This value here is no longer 211, right? But rather what's being passed in is the address for A in main. Right, so there's a different picture now.
No longer an int a, it's now an int a pointer
In main, or so in main, let's look at this line that I highlighted here. Right, so back in main, I've got diagramming procedurally, right, step by step. We've got a methodology here. Int A is 211. Its address, we don't know, but we can print it out, right? And indeed, we do print it out, and it gives us this address value.
Oh, so that's interesting.
Yeah. And then we proceed to call into swap pass by references here. We're now in this frame here, and let's jot down everything that it will tell us following our methodology, right? So we've taken care of A pointer. B pointer is the other argument. Its data type is int star. Variable name is B pointer. Where does it live? Doesn't matter too much. We could find out. right? But another tweak, this is now 8 cells tall. And what's being passed in is no longer the value of B, but rather where B lives, right? And we know that. We can put that here. Okay, so we also have this line of code, right? This line of code on 219 can be diagrammed out too. And we have that to this effect. So we've got int is the data type, temp is the variable name, and what do we store into this value? How do I interpret what's being highlighted here under the cursor? Yeah. Oh, you go first. Good, right? So what's being referred to is B pointer. B pointer is this value here, and star chases the pointer, right? Star goes from addresses to the content. So where is this pointing to?
The contents of B pointer.
Contents of B pointer, it's this address here. We can look at it in the Excel sheet, and there, it's in main, right? So it's gonna go back into the main function, dereference it, get 422, and jot that down, right? So that's what's happening on 219. 220,
The contents of B pointer are being exchanged with the contents of what are at A pointer, which I assume is 211.
so it's gonna grab the contents of A pointer, so dereference A pointer. What's A pointer? It's this value. We can now look it up in the Excel sheet, if I didn't mess it up too much. Oh, come on. It's going to be down here, so get the dereference value of A pointer, which is 211, and where to put it. It's going to put it at the dereferenced value of B pointer. So it's going to chase down B pointer, which points to here, dereference it, look at its contents, and write down the value that it grabbed, 211, right? So 211 shows up here, and we're done with line 220, and line 221.
It will set the contents of A pointer to whatever was in 10.
So again, chase down A pointer, which is over here, and it will write to the location pointed to by A pointer the value 422. And we're done, right? So here we're done with pass by references. And what does it mean to be done with the function? We pop it off the stack, right? It's the stack. We remove it from the stack. We're back now in main. And in main, we'll print out A and B here. And what's in A? 422. B is 211. It succeeds. Right? So that's just a very tedious work through of exactly how this is happening. Right? By passing in pointers, we're able to manipulate data that was on the calling function, in this case, the main function. And just to complete the example, let's go ahead and run. And run. And lo and behold, it succeeds in swapping. Okay, so let's change gears. 2 minutes of any questions here before I change gears. Okay, how many of you have attempted edit distance? Part 2 of programming assignment 1. How many are done with edit distance? 1. So how did you tackle edit distance?
I used it's a dynamic programming formula. It's basically I made a 2D array, and
Okay, good, right? So you get at the point of there has to be a 2D array, which is fortunate because today we learned everything there is to know about 2D arrays. So let's work through what the edit distant task is all about. Okay, edit distance. Suppose I have two strings, right? Cat and tact. What's the edit distance between these two strings? Minimum edit distance. Yeah. 2. How do you figure it's 2? So the edit distance here is 2, right? So C changes to T, and we inserted a C between A and T. So we get tact, right? And this is intuitive, and we can just kind of eyeball this when the examples are small. But when the examples are big, we need an algorithm to figure that out, right? And a valid algorithm is called, I forget what the algorithm is called, right? But we'll work through it now. There's a recursive algorithm. What it does is it checks if the first characters match. If they match, great, the cost is 0. If they don't match, then the cost is 1. And then it considers what's the cost of the rest of the substring. So it's a recursive algorithm that requires us to figure out all the costs of the minimum substrings and then looks across all of them and finds the minimum total cost. It's helpful to work through an example here, right? So let me work through an example of what's the edit distance between it and int. Right, what's the edit distance of it and int? It's just 1, right? You insert a n between I and t. And the way the algorithm is going to figure this out is it considers 3 possibilities. Right? The 3 possibilities here are maybe you deleted a character, maybe you modified a character, or maybe you inserted a character. Right? So delete, modify, insert. So if you deleted a character, then it considers that you deleted a character, therefore leading to the next string. The other alternative is maybe you modify the character, therefore leading to the next string. Or maybe you inserted a character, right? And we represent inserted characters like this. Okay, and is this enough to figure out what the minimum distance is yet? We don't know, right? We have to iterate on the substrings. So by iterating on the substrings, I mean we've taken care of the first characters, and now we're going to recurse the problem on the remaining substrings. So the next layer down, we skip the first character and consider the minimum edit distance on the remaining substring. And again, right, this time around, we consider 3 possibilities. Do we delete a character, modify a character, or insert a character? So again, 3 cases. Right, so 3 cases here would be maybe I deleted a character, maybe I modified a character, maybe I insert a character. Same thing, next subtree, maybe I delete a character, maybe I modify a character, maybe I insert a character. Finally, third subtree, right? Maybe I delete a character, maybe I modify a character, maybe I insert a character. And then we continue to recurse, right? So we get rid of the first character, and each of these problems continue on to the next layer down. So what's the downside of all of this? Right, I'm going to expand this next subtree here to illustrate what's the downside here. Right, each subtree, again, maybe you delete a character, maybe you modify a character, maybe you insert a character. So who's noticed something interesting happening here already? So this subtree that I draw here, does this have to be evaluated somewhere else in this algorithm? Right, notice how what I highlighted in blue is exactly the same computation that has to be done here. Right, it's comparing t versus nt. Right, so this is the reason why this purely recursive algorithm is inefficient. Right, we're going to expand all these subtrees, but there's going to be a lot of replicated work if we just naively kind of keep expanding. Right, and if you run the edit distance provided code, the edit distance provided code implements this. Right, you can study how the dynamic programming recursive code works, and the picture that it's drawing is this picture here. But does that solve the assignment? Who's run it already and see what happens? Yeah, what happens?
Yeah, it just times out because the recursion takes too long.
Yeah, the times out because the recursion takes too long, right? This is fine for really tiny examples, 3, 4, 5 characters, but the test cases go up to, I don't know, 16 characters, and this is going to be a gigantic tree that it's not able to travel through, right? And maybe just to close out this picture, right? How does this picture arrive at the conclusion that the edit distance is 1? Right, so the annotation here would be, okay, the cost of insertion here was 1. Cost of insertion or modification here is 0 because I matches I, so this is no cost here. And the cost of deletion here is +1. Here, there's a cost of +1 because we insert n on the bottom. And then on that next level down, we got +0 from t matches t. Right? So in other words, this recursive algorithm would have figured out that the total cost of editing from it to int is 0 + 1 + 0 = 1. This is the minimum cost. Right? If you wanted to study how this algorithm works. And it's very cool. But your task, right? Your task is something slightly different. Your task is to help this algorithm work well, right? To be able to tackle the bigger problems. So how might we do that? What was the main problem of the original naive algorithm? It's repeating a lot of work, right? So we want to record down information so that it doesn't repeat that work. And there's an algorithm that you can look up, which I think the assignment description should hint at. What's the algorithm called? Yeah. No, Levenstein's the edit distance. This is the edit distance, Levenstein edit distance. There's a tabular algorithm called, it's called Wagner-Fisher. Which you should, you know, if these notes don't make sense, you should look it up. And the way that the Wagner-Fisher distance, or Wagner-Fisher function or algorithm for finding Levenstein edit distance, it makes a table, right? It makes a 2D array, which is great. Today we learned how to program 2D arrays in C, so this is a great exercise on that. And the way it's going to do this is you've got your input string, you've got your destination string. So you want to see what's the edit distance to go from it to int. And it builds a table. Hold on, let me just rewrite this. So it builds a table. It considers the possibility first of maybe there was a blank before the strings, right? So that's why we added additional blank beforehand. And it will write down 0. And the rule for how it does this evaluation, right? It's a row by row, column by column approach, is it will look at the character I versus blank. If they don't match, that's +1. +1 to what? +1 relative to the minimum number that you can use to get to that point, right? So in this case, the only filled out element was 0. So it's 1 plus 0, it writes down a 1 here, right? And then it keeps going. Then it asks, do T and blank match? No, right? So that's another +1. It writes down 1 plus 1 is 2 here. So we're done with the first row. The second row, same question. It asks, does blank and I match? No, right? So that's a +1 to here. Then it asks, does I and I match? Yeah, it matches. So it's a 0. 0 relative to what, right? So the very critical piece now is it's going to +0, and it will consider all the ways to get to this cell from the above to the left and also diagonal. And the minimum way to get here so far is this 0 there. So it will record 0 plus 0, you will jot down 0 here, right? So far to match strings, blank I, no edits so far. So you're able to match blank I and blank I with 0 cost, right? Got 3 more minutes. I can finish this example, all right? So what's the next step? Row by row, column by column. What to compare next? Yeah. Yeah, it will compare T and I. Do they match? No, it's +1. +1 relative to what? So the cheapest way to get here so far is that 0 to the left. So 0 plus 1 is 1 here, and we're done with this row. What to consider next? Blank versus n. Do they match? No. Cost is +1. +1 relative to what? No. +1 relative to the above, right? The cheapest way to get to this cell is from above.
I thought we were going diagonal.
Diagonal, there is no diagonal here.
Oh,
At this point, there is no diagonal.
we're not counting that 0 to be diagonal from.
No. No. So we're still in the first column. So the cheapest way to get to this cell of blank and n is from above, and they don't match, so now it's +1 is 2. I and n, do they match? No. And so it's +1 relative to, so +1 there. And finally, T and n, do they match? No. So it's +1 relative to where?
0.
Yeah, you've got an option to get to there from 0. Oh no. I've got an option to get to there from 0. And so 1 there. 1 more minute left. Okay, blank and t, do they match? No, so it's +1 relative to 3 there, good. And I and t, do they match? It's +1 relative to above, so it's 2, good. And finally, t and t, do they match? Perfect, so +0 relative to where? So you can get to there from either of these, so it is 1 plus 0 is 1. So we conclude that the edit distance of IT versus INT is just 1. Yeah,
So you're just looking at the last row and seeing which number is the smallest.
that's right. Yeah. Right, and this is just working through an example to fully kind of, if you want to refer to notes on how this works, this is the keyword that you want to search for. But this is the table that you want to write down, and all the data inside this table really is just memoizing or recording the calculations of this recursive approach, right? And so it's able to run a lot faster. All right, good luck.